Hi, I'm Quinn, and today's Daily Quantum Byte episode we're unpacking Bell's inequality. Bell's inequality sounds intimidating, but the idea is beautifully simple. John Bell's insight was to calculate that limit. If the world is governed by local hidden variables, correlations can't go past a certain line. Quantum mechanics predicts they can. That's the whole story. In a Bell test, you create an entangled pair, send each particle to a faraway detector and randomly choose measurement settings. When you compare the outcomes later, the correlations violate Bell's inequality, exactly as quantum theory predicts. Does that mean faster-than-light messaging? No. Each observer still sees random results. The spooky correlation only appears once you compare notes. So Bell violations don't break relativity. They just rule out a purely classical explanation. Hey, picture this. You have a friend. Let's call her Alice. And Alice has this weird habit. Every morning she reaches into her drawer without looking and pulls out 2 socks completely at random. Sometimes she gets 2 red socks. Sometimes 2 blue. Sometimes 1 of each. Now here's where it gets interesting. Alice lives far away, so she mails 1 sock to her friend Bob every single day. He keeps the other sock for herself. When Bob opens his package each day, he finds either a red sock or a blue sock. And here's the question that's going to unlock everything. Are the colors of these socks determined the moment Alice pulls them from the drawer? Or do they somehow decide their colors only when Alice and Bob actually look at them? You might think, of course they're determined when she pulls them out. That's ridiculous. Now let's make this a bit more interesting. Imagine Alice doesn't just randomly grab socks. Instead, she has a magical drawer that somehow produces correlated sock pairs. Here's what we observe. Whenever Alice looks at her sock and Bob looks at his sock at the exact same angle, let's say they both check if it's red or blue, they always get opposite results. Alice gets red, Bob gets blue. Alice gets blue, Bob gets red. Every single time. That is weird. But we can explain it with local realism, right? Maybe the drawer secretly prepares the socks with opposite colors beforehand. Like a pre-programmed instruction, this pair, Alice gets red, Bob gets blue. But now, and this is crucial, what if Alice and Bob can measure their socks at different angles? Not just is it red or blue, but maybe, is it red or blue when tilted 30 degrees, or when tilted 60 degrees? If the socks have definite, predetermined properties, we can write down little instruction cards for each sock pair. Like, at 0 degrees, Alice sees red, Bob sees blue. At 30 degrees, Alice sees blue and Bob sees red. At 60 degrees, Alice sees red, Bob sees blue. Here's where John Stuart Bell comes in with a stroke of genius. In 1964 he said, if these instruction cards exist, if local realism is true, then there's a mathematical limit to how correlated Alice and Bob's results can be when they measure at different angles. He worked out the math and it gives you something called Bell's inequality. Think of it like this. If you measure at 3 different angles, let's call them A, B, and C, and you count how often Alice and Bob get different results, local realism says differences between A and B, plus differences between B and C, is greater than differences between A and C. It's kind of like saying, the number of people who like apples but not bananas plus the number who like bananas but not cherries must be at least as many as those who like apples but not cherries. It's just basic logic. Basic arithmetic. And if the socks are carrying instruction cards, this inequality must be true. So what happens when we actually do this experiment? Not with socks, obviously, but with entangled photons or electrons, the quantum version of our magic socks. Nature breaks Bell's inequality. And it doesn't just barely break it, it shatters it. When physicists measure entangled particles at different angles, they find correlations that are stronger than any instruction card system could ever produce. The quantum correlations are too powerful, too perfect, to be explained by predetermined properties. This means one of 2 things has to be true, and both are completely wild. Option 1. The particles don't have definite properties until you measure them. The sock isn't red or blue until Bob opens the package. Reality is fundamentally indeterminate. Option 2. The particles communicate faster than light. When Bob measures his sock in Tokyo, it instantly affects Alice's sock in New York, violating Einstein's cosmic speed limit. Most physicists accept option 1. The universe really is weird in a deep, fundamental way. Here's the thing. Bell's inequality isn't just philosophical navel-gazing. It's been tested experimentally thousands of times with photons, electrons, even atoms. And every single time, quantum mechanics wins. Local realism loses. This has real consequences. It means the universe doesn't work like tiny billiard balls with hidden properties. Quantum encryption is possible because nature can't be eavesdropped on classically. There are correlations in nature stronger than anything classical physics allows. Why does this matter for quantum computing? Because it's experimental proof that entanglement is real and operational. It means quantum devices can produce correlations that no classical device can mimic. That's the foundation for quantum communication, quantum cryptography, and the entangling gates that power algorithms. So the big takeaway is this: Bell's inequality is the line that classical physics can't cross. Entanglement crosses it, and that's why the quantum world is fundamentally different. That's all for today. Take care.